welcome to this problem walkthrough. Today, we'll explore an interesting challenge titled Subarray Sum equals k. This problem is a popular choice for testing algorithm design, efficiency, and optimization skills. Let's dive into the details and break it down step by step. In this problem, you are given an array of integers called nums and a target integer k. The task is to determine how many continuous subarrays within nums have a sum that is exactly equal to k. A subarray is defined as a contiguous portion of the array, meaning the elements must appear consecutively in their original order. The output should be an integer representing the total count of such subarrays. For example, if the input array is 1, 1, 1, and the target k is 2, you need to identify all subarrays that add up to 2. We'll look at some examples to better understand this requirement. For the input nums equals 1, 1, 1, and k equals 2, the output is 2. This is because there are two subarrays whose sum equals 2. The first subarray is 1, 1, starting at index 0 and ending at index 1. The second subarray is also 1, 1, but this one starts at index 1 and ends at index 2. Both satisfy the condition since their sums are equal to k. Another example is nums equals 1, 2, 3, with k equals 3. Here, the output is also 2 because the subarrays 1, 2, and 3 both sum to 3. These examples demonstrate how to count subarrays that meet the specified condition. In the example where nums equals -1, -1, 1, and k equals 0, the output is 1. The only subarray that sums to 0 is the entire array itself, -1, -1, 1, which starts at index 0 and ends at index 2. This highlights that subarrays can include negative numbers and that the entire array can also be considered a valid subarray. These examples illustrate the diverse scenarios that can arise, such as arrays with negative numbers, subarrays of different lengths, or even cases where the target sum is 0. The solution must account for all of these possibilities. This problem also comes with constraints and edge cases that need to be handled carefully. The array nums can have up to 10,000 elements, and each value within nums can range from -10,000 to 10,000. The target sum k can also be very large, ranging from -10,000,000 to 10,000,000. Edge cases include scenarios like a single element array, where a match with k results in one valid subarray, or no match results in 0. Arrays with all negative numbers must be handled correctly as well. Additionally, the algorithm should scale efficiently for large inputs, such as arrays with tens of thousands of elements. Special cases include target sums of 0, which require careful handling to ensure that subarrays summing to 0 are correctly counted. Finally, arrays with repeated numbers might form overlapping or distinct subarrays that meet the target, and the solution must account for all valid combinations. To tackle the problem of finding subarrays whose sum equals a given value k, we can start with the most straightforward approach, the brute force method. The intuition here is simple: enumerate all possible subarrays in the array nums and calculate their sums one by one. For each subarray, we check if the sum equals k. This can be implemented using two nested loops, where the outer loop fixes the starting point of the subarray, and the inner loop extends the subarray to include additional elements. Each time we calculate the sum, we verify if it matches k and increment our count accordingly. While this method is easy to understand and implement, it has a major drawback: the time complexity. Since we use nested loops to iterate through all possible subarrays, the approach has a time complexity of n squared. On the bright side, the space complexity is minimal, just 1, as we don't use additional memory structures. However, this inefficiency in runtime makes it impractical for large input sizes. The brute force method, while intuitive, has significant limitations due to its quadratic time complexity. For larger arrays, this approach quickly becomes too slow. To overcome this inefficiency, we can turn to an optimized solution that leverages a hash map. The key insight here is based on cumulative sums, also known as prefix sums. The idea is that if the sum of a subarray from index I to j equals k, then the cumulative sum up to index j minus the cumulative sum up to index I must equal k. By rearranging this equation, we can see that if we know the current cumulative sum and the value of the cumulative sum that would lead to a subarray sum of k, we can determine if such a subarray exists. To achieve this, we use a hash map to store the frequency of each cumulative sum encountered so far. As we iterate through the array, we compute the current cumulative sum, check if the difference between the current sum and k exists in the hash map, and if so, add the frequency of that difference to our count. This approach significantly reduces the runtime by eliminating the need for nested loops. In the implementation of the hash map approach, after checking for the difference between the current cumulative sum and k, we update the hash map to include the current cumulative sum. If the current sum already exists in the hash map, we increment its frequency, otherwise, we initialize it with a frequency of 1. This ensures that we correctly track all prefix sums as we traverse the array. The optimized solution has a time complexity of O(n), as we make a single pass through the array and each hash map operation, whether it's a lookup or an update, takes constant time. The space complexity is O(n), because we store the cumulative sums in the hash map. While this method is much faster than the brute force approach, it does require additional memory, which may be a concern in environments with limited resources. Nonetheless, the trade-off is worthwhile for the dramatic improvement in efficiency. It's also worth noting that alternative strategies like the sliding window technique are ineffective here, as they rely on all elements being non-negative, which is not guaranteed in this problem. With negative numbers in the array, the sliding window cannot reliably track subarray sums. The hash map approach stands out as the most efficient and versatile strategy for solving this problem. Its O(n) time complexity ensures it can handle large input sizes with ease, and it works seamlessly with arrays containing both positive and negative numbers. The core insight, the relationship between prefix sums and subarray sums, is what makes this method so powerful. When compared to the brute force approach, the hash map solution eliminates the need for nested loops, reducing the time complexity from O(n)² to O(n), which is a dramatic improvement. Unlike the sliding window technique, which fails in the presence of negative numbers, the hash map approach remains robust and reliable. While it does require additional memory to store the hash map, this is a reasonable trade-off for the substantial gains in runtime efficiency. Overall, the hash map solution strikes the right balance between speed and memory usage, making it the best choice for this problem. The problem asks us to find the total number of continuous subarrays in an array that sum up to a given integer, k. To start, we can use a brute force approach. This involves iterating over all possible subarrays and calculating their sums to check if they match k. First, we initialize a variable, count, to 0. This will keep track of the total number of subarrays we find that meet the condition. Then, we use two nested loops. The outer loop iterates through each index I in the array, treating it as the starting point of a subarray, while the inner loop iterates through all possible ending points j for the subarray starting at I. The idea is to explore every possible subarray by varying both the starting and ending indices. For each subarray defined by the indices I and j, we calculate the sum of the elements from nums I to nums j. If the sum of the current subarray equals k, we increment the count variable by 1. This process ensures that we consider every possible subarray in the array. After completing the nested loops, we simply return the final value of count, which represents the total number of subarrays that satisfy the condition. While this approach is straightforward and easy to implement, it is computationally expensive due to the nested loops. The need to calculate the sum for each subarray makes it inefficient for larger arrays. The Python implementation here demonstrates the brute force solution, where we maintain a running sum within the inner loop and increment the count whenever we find a matching subarray. The brute force approach has a time complexity of O(n)², because we use two nested loops to iterate through all possible subarrays. This makes it impractical for large arrays. The space complexity, however, is O(1), as no additional data structures are used. To improve efficiency, we can use an optimized approach that leverages the prefix sum technique in combination with a hash map. The key insight behind this optimization is that the sum of a subarray can be expressed using prefix sums. Specifically, if the cumulative sum up to index j is prefix_sum, j, and the cumulative sum up to index I1 is prefix_sum, I1, then the sum of the subarray from I to j is simply the difference, prefix_sum, j, prefix_sum, I1. If this difference equals k, we know the subarray from I to j has the desired sum. Rearranging the equation, we can see that for each prefix_sum, j, we need to check whether prefix_sum, j, k exists in a hash map that stores previous prefix sums. This allows us to efficiently find subarrays with the desired sum. To implement the optimized approach, we start by initializing a hash map called prefix_sums to store the frequency of prefix sums. We also initialize it with the entry 0, 1 to handle cases where a subarray starting from index 0 sums to k. Additionally, we define two variables, prefix_sum to keep track of the running sum as we iterate through the array, and count to store the number of valid subarrays. As we process each element in the array, we add the current element to prefix_sum. Next, we calculate the complement, which is prefix_sum k. If this complement exists in the hash map, it means there are one or more subarrays ending at the current index whose sum equals k. In that case, we add the frequency of the complement in the hash map to the count variable. This step ensures that we efficiently account for all possible subarrays without needing nested loops. After checking for the complement, we update the hash map by incrementing the frequency of the current prefix_sum. This ensures that the hash map always reflects the prefix sums encountered so far. Once we finish iterating through the array, we return the count, which represents the total number of subarrays that sum to k. The Python implementation here demonstrates the optimized approach. By maintaining a hash map of prefix sums and their frequencies, we avoid the need to explicitly calculate the sum of every possible subarray, drastically reducing the computational cost. This makes the algorithm not only faster but also more scalable for larger input sizes. The optimized approach offers several key advantages. First, the hash map enables constant time lookups for the complement, significantly improving efficiency compared to the brute force method. Second, this approach handles arrays with negative numbers seamlessly, as the hash map keeps track of all prefix sums regardless of their sign. Additionally, it accounts for edge cases, such as when the input array is empty, in which case the function correctly returns 0. It also works when all elements in the array are negative or 0, ensuring accurate results in such scenarios. The use of a hash map is central to this method, as it provides an efficient way to store and retrieve prefix sums. In terms of complexity, the algorithm runs in O(n) time, where n is the length of the array, because each element is processed once and hash map operations are O(1) on average. The space complexity of the optimized approach is O(n), as we use the hash map to store prefix sums. This storage grows proportional to the number of unique prefix sums encountered during the iteration. To better understand how this works in practice, let's walk through an example. Suppose the input is nums equals 1, 2, 3, and k equals 3. We initialize the hash map with 0, 1, and both prefix_sum and count are set to 0. As we iterate through nums, we first process the element 1, updating prefix_sum to 1. The complement, 1 to 3, equals -2, which is not in the hash map, so no subarrays are counted yet. We then update the hash map to include the current prefix_sum. Next, we process the element 2, updating prefix_sum to 3. The complement, 3 to 3, equals 0, which does exist in the hash map with a frequency of 1. This means there is one subarray summing to k so far, so we increment count to 1. After updating the hash map, we move to the final element, 3. Here, prefix_sum becomes 6. The complement, 6 to 3, equals 3, which is in the hash map with a frequency of 1. We increment count to 2, reflecting the two subarrays that sum to k, 3, and 1, 2. Finally, we return the count, which is 2. In conclusion, the optimized algorithm using prefix sums and a hash map provides a significant performance boost over the brute force approach. By reducing the time complexity from O(n) squared to O(n), it becomes suitable for handling large arrays efficiently. The algorithm is not only efficient but also robust, handling edge cases and negative numbers with ease. This combination of speed, clarity, and correctness makes it an excellent solution for the problem of finding subarrays that sum to a given value, k. The provided Python implementation solves LeetCode problem number 560, subarray sum equals k using a prefix sum and hash map approach. This achieves an efficient O(n) time complexity, where n is the length of the input array. Explanation. 1. Initialization. Count is initialized to 0 to store the number of subarrays whose sum equals k. Current_sum is initialized to 0 to keep a running total of the array elements as we iterate.
prefix underscore sums is a dictionary initialized with 0, 1.
This handles the edge case where a subarray starting at index 0 has a sum equal to k.
2. Iterating through the array. For each element number in the array, update current underscore sum by adding number to it. Check if current underscore sum k exists in the prefix underscore sums dictionary.
If it does, it means there is a prefix sum that, when subtracted from the current sum, equals k. The value associated with current underscore sum k in prefix underscore sums gives the count of such prefix sums.
Add this count to count. 3. Updating the prefix sums dictionary. After processing number, update prefix underscore sums with the current sum.
If current underscore sum is already a key in prefix underscore sums, increment its value. Otherwise, add it as a new key with a value of 1.
4. Return the result.
After iterating through the array, return the value of count, which represents the total number of subarrays with a sum equal to k.
#### key insights.
By using a hash map to store the prefix sums, we avoid the need for nested loops, reducing the time complexity from O(n) squared in a brute force solution to O(n). The hash map keeps track of how many times each prefix sum has occurred, enabling quick lookups to calculate the number of valid subarrays. This implementation handles edge cases such as negative numbers, zeros, and subarrays starting at index 0, making it robust and efficient for all valid inputs. This is the Java implementation for LeetCode problem number 560, subarray sum equals k. The logic mirrors the Python implementation, using a hash map to store prefix sums and their frequencies. The subarray sum method iterates through the input array, updating the current running sum and checking if a previous prefix sum exists such that the difference equals the target k. Key differences include explicit type declarations and Java-specific collections like hashmap. The method efficiently solves the problem with O(n) time complexity by leveraging the prefix sum approach. In this example, we are given an array nums with values 1, 1, 1, and a target sum k equal to 2. The goal is to determine how many subarrays have a sum equal to k. To solve this, we initialize 3 variables: count, which will hold the number of valid subarrays and starts at 0, current underscore sum, which keeps track of the cumulative sum as we traverse the array and also starts at 0, and prefix underscore sums, a dictionary that maps cumulative sums to their frequencies. We initialize it with 0, 1 to account for subarrays starting at index 0. During the first iteration, the current number is 1. Adding this to current underscore sum gives us 1. We then check if the difference current underscore sum k, which is 1 to 2 or minus 1, exists in the prefix underscore sums dictionary. Since it does not, count remains 0. Finally, we update prefix underscore sums to include the new current underscore sum, so it becomes 0, 1, 1, 1. In the second iteration, the current number is again 1. Adding it to current underscore sum gives 2. We then check if current underscore sum k, which is 2 to 2 or 0, exists in prefix underscore sums. It does, and the value associated with 0 in prefix underscore sums is 1. This means there is one subarray ending at the current index with a sum equal to k, so we increment count by 1, making it 1. Next, we update prefix underscore sums to include the new current underscore sum, resulting in 0, 1, 1, 1, 2, 1. In the third iteration, the current number is again 1. Adding this to current underscore sum gives 3. Checking current underscore sum k, which is 3 to 2 or 1, we find that 1 exists in prefix underscore sums with a value of 1. This indicates another subarray with sum equal to k, so we add 1 to count, making it 2. We then update prefix underscore sums to 0, 1, 1, 1, 2, 1, 3, 1. The final result is count equals 2, meaning there are 2 subarrays with sums equal to k, 1, 1, at indices 0, 1, and 1, 1, at indices 1, 2. In the second example, nums is 1, 2, 3, and k is 3. We start by initializing the same variables, count at 0, current underscore sum at 0, and prefix underscore sums as 0, 1. For the first iteration, the current number is 1. Adding it to current underscore sum gives 1. Checking current underscore sum k, which is 1 to 3 or minus 2, we find that minus 2 does not exist in prefix underscore sums, so count remains 0. We then update prefix underscore sums to include the new current underscore sum, resulting in 0, 1, 1, 1.
In the second iteration, the current number is 2. Adding it to current underscore sum gives 3.
Checking current underscore sum k, which is 3 to 3 or 0, we find that 0 exists in prefix underscore sums with a value of 1. This means there is one subarray ending at the current index with a sum equal to k, so we increment count by 1, making it 1. Next, we update prefix underscore sums to include the new current underscore sum, resulting in 0, 1, 1, 1, 3, 1.
In the third iteration, the current number is 3. Adding it to current underscore sum gives 6.
Checking current underscore sum k, which is 6 to 3 or 3, we find that 3 exists in prefix underscore sums with a value of 1. This indicates another subarray with sum equal to k, so we add 1 to count, making it 2. We then update prefix underscore sums to 0, 1, 1, 1, 3, 1, 6, 1. The final result is count equals 2, meaning there are 2 subarrays with sums equal to k, 1, 2, at indices 0, 1, and 3, at index 2. In the third example, nums is -1, -1, 1, and k is 0. We again initialize count at 0, current underscore sum at 0, and prefix underscore sums as 0, 1.
For the first iteration, the current number is -1. Adding it to current underscore sum gives -1.
Checking current underscore sum k, which is -1 to 0 or -1, we find that -1 does not exist in prefix underscore sums, so count remains 0. We then update prefix underscore sums to include the new current underscore sum, resulting in 0, 1, -1, 1.
In the second iteration, the current number is again -1. Adding it to current underscore sum gives -2.
Checking current underscore sum k, which is -2 to 0 or -2, we find that -2 does not exist in prefix underscore sums, so count remains 0. We then update prefix underscore sums to include the new current underscore sum, resulting in 0, 1, -1, 1, -2, 1.
In the third iteration, the current number is 1. Adding it to current underscore sum gives -1.
Checking current underscore sum k, which is -1 to 0 or -1, we find that -1 exists in prefix underscore sums with a value of 1. This indicates one subarray with a sum equal to k, so we increment count by 1, making it 1. We then update prefix underscore sums to 0, 1, -1, 2, -2, 1. The final result is count equals 1, meaning there is one subarray with a sum equal to k, -1, 1, at indices 1, 2. Here, we analyze the time complexity of our solution, which is O, n, where n is the length of the input array. This efficiency comes from the fact that the algorithm processes each element of the array exactly once in a single loop. For every iteration, updating the current underscore sum is done in constant time, O1, as it involves a simple addition. Checking whether current underscore sum k exists in the prefix underscore sums dictionary is also a constant time operation, thanks to Python's efficient hash table implementation. Additionally, updating the dictionary, whether by adding a new key or incrementing an existing one, also occurs in O1 time on average. Since these constant time operations are repeated for each element, the overall time complexity is O(n). Regardless of the input, whether it's the best case, average case, or worst case, the algorithm processes each array element once, maintaining the O(n) complexity. Now, let's consider the space complexity of the solution, which is O(n) in the worst case. This is primarily due to the prefix underscore sums dictionary. The size of prefix underscore sums depends on the number of unique cumulative sums encountered during the loop. In the worst case scenario, such as when the array consists of all positive or all negative numbers, the cumulative sums will all be unique, leading to O(n) additional space usage. On the other hand, if there are repeated cumulative sums that cancel each other out, the dictionary may remain small, and space complexity can approach O(1). Beyond the dictionary, other variables like count and current underscore sum use a constant amount of space, O(1). Therefore, the overall space complexity is dominated by the dictionary and is O(n) in the worst case. Let's compare this optimized approach to the naive solution. The naive method involves iterating over all possible subarrays and calculating their sums. This requires an outer loop to iterate through all starting indices of the subarrays, which takes O, n, and an inner loop to iterate through all ending indices, which also takes O, n, in the worst case. Multiplying these together gives a total time complexity of O, n squared. However, the naive approach has a space complexity of O, 1, as it doesn't use any additional data structures. In contrast, the optimized approach significantly improves the time complexity, reducing it from O, n squared to O, n, by leveraging a hash table to store cumulative sums and check conditions in constant time. The trade-off is a slight increase in space complexity to O, n, due to the use of the hash table. To mathematically confirm the time complexity of the optimized approach, consider that the algorithm performs n iterations of the loop, where n is the size of the input array. During each iteration, dictionary operations such as lookups and updates are performed. These operations have an average time complexity of O, 1. Therefore, for the entire algorithm, the total time complexity is n iterations multiplied by the O, 1, cost of each dictionary operation, resulting in O, n. This efficient combination of linear iteration and constant time dictionary operations ensures that the overall complexity remains O, n. When tackling the subarray sum equals k problem, there are a few common mistakes to watch out for. First, a frequent error is not accounting for negative numbers in the array. If you assume all the numbers are non-negative, your algorithm might fail when the input includes negative values. To fix this, always check that your solution can handle both positive and negative numbers when calculating subarray sums. Another mistake is overlapping subarrays or double counting. This happens when the same subarray is included multiple times, leading to incorrect results. To address this, use strategies like sliding windows or hash maps to ensure each subarray is counted only once. Finally, many people rely on a brute force approach, iterating through all possible subarrays and calculating their sums directly. While straightforward, this results in O, n squared, or even O, n cubed, time complexity, which becomes impractical for large arrays. Instead, optimize your solution by leveraging techniques like prefix sums or hash maps, which reduce the time complexity to O, n. Now, let's look at some additional tips and variations. Handling edge cases is critical. Ignoring scenarios like empty arrays, arrays with all zeros, or cases where k equals 0 can lead to unexpected bugs. To prevent this, write test cases specifically for these situations and ensure your solution handles them correctly. Another common issue is misinterpreting the problem statement. For example, you might assume the task involves contiguous subarrays when it could allow for non-contiguous subsets. Always read the problem carefully to confirm the requirements. From an interview perspective, recognizing patterns is key. Many subarray problems can be solved using techniques like prefix sums or sliding windows, so identifying these quickly can save time. Interviewers also appreciate a structured approach, starting with a brute force solution and then optimizing it. Clearly explaining your thought process, addressing edge cases, and discussing trade-offs between time and space complexity will showcase your problem-solving skills effectively. There are also related problems and alternative solutions worth exploring. Some related problems include LeetCode 560 itself, as well as LeetCode 325, which asks for the maximum size subarray with a given sum, LeetCode 523, which focuses on continuous subarrays with a sum that is a multiple of a given number, and LeetCode 930, which deals with binary subarrays with a specific sum. Exploring these can deepen your understanding of subarray problems and their variations. When it comes to alternative approaches, prefix sums combined with a hash map are a popular choice. This method achieves O, n, time complexity and O, n, space complexity, making it efficient for large inputs. However, the trade-off is the additional memory required for the hash map. Another option is the sliding window technique, which can also achieve O, n, time complexity with O, 1, space complexity under certain conditions, such as when the input contains only positive numbers. Keep in mind, though, that sliding windows are less effective when negative numbers are involved. Lastly, there are other approaches like brute force and divide and conquer, each with their own trade-offs. The brute force method involves iterating through all subarrays, calculating their sums directly. While it's simple to implement, it has a time complexity of O, n squared, to O, n cubed, making it impractical for larger input sizes. On the other hand, divide and conquer offers a more balanced approach with a time complexity of O, n log n, and a space complexity of O, log n, due to the recursion stack.
However, it's more complex to implement and isn't as commonly used for subarray problems.
Understanding these trade-offs is important, as the best approach depends on the specific constraints and requirements of the problem you're solving. By considering these factors, you can choose the most effective solution for the given context.
Great work!
We've reviewed the problem subarray sum equals k and explored how to efficiently solve it using a hash map approach.
Remember the key takeaways about utilizing cumulative sums for optimization.
Thanks for joining, and don't forget to practice similar problems to strengthen your skills.
See you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!